Okay, let me begin by way of review. So far, what we have done, oh wait, I don't think you can see the screen. Okay, I hope you can see the screen now. I'm showing the Excel file we were working on last time. So just by way of quick review, we learned that matrices are just a collection of numbers. So we identify matrices usually by a letter, capital letter, but you can name it otherwise. And we identify its dimension by the number of rows and columns. And we said that matrices can be added or subtracted. You can add matrices for as long as they have the same dimension. A 4 by 3 column matrix with a 4 by 3 matrix, a 6 by 6 matrix can be added to a 6 by 6 matrix. And the order does not matter because it's addition. It's actually a scalar addition. So A plus B, for example, if two matrices A plus B, in this case, it's 4 by 3 and 4 by 3, then these two matrices are, you can add these two matrices. And in our discussion last time, so we called it C, and we just use the sum function in Excel. Okay, so you can also subtract two matrices if they have the same dimension. So 6 by 2 matrix, matrix D, and matrix E 6 by 2, we can create a matrix F, which is just the difference of those two matrices. We can subtract them. All right. Now, we also discussed the multiplication of matrices, and we said that the matrix multiplication follows a particular rule. So we said that two matrices are multiplicable if the column of the first matrix is the same as the row of the second matrix. And the resultant matrix is the row of the first one and the column of the second one. So for example, we have a 3 by 2 matrix, matrix G, and a 2 by 3 matrix, matrix P. G and P, G can be multiplied to P. Okay, they are multiplicable because the column of the first matrix is the same as the row of the second matrix, and the resulting matrix is 3 by 3. Now, there is no commutativity as far as matrix multiplication is concerned. So GP is not the same as PG. In fact, it's possible that PG may be not multiplicable. But in this case, P is 2 by 3 and G is 3 by 2, then they are still multiplicable. And the resulting matrix is 2 by 2, which is your P times G. But you notice that G times P has a dimension 3 by 3, and P times G has a dimension 2 by 2. Therefore, we say that these two matrices are not equal, they're not equivalent. Okay, we gave an example last time, A times B, where A times B is multiplicable because the column of matrix A is the same as the row of matrix B, and the resulting matrix is 3 by 1. However, B times A is not multiplicable because of the rule that we just mentioned. So there's no commutativity as far as matrix multiplication is concerned. Okay, we also learned how to define the transpose of a matrix. The transpose of the matrix is just the row becoming the column and the column becoming the row. So for example, this is the first row is 3, 6, 7. If you get the transpose of this whole matrix, then this row 3, 6, 7 will become the column 3, 6, 7. Okay, and the size will be converted also. This is a 4 by 3 matrix. This one now becomes a 3 by 4 matrix. So we also looked at an identity matrix where it's a matrix, it's a square matrix, meaning the rows and columns are the same. and all the diagonals are 1, and the rest are 0. So for example, this is an I3, which means we just indicate the row because an identity matrix will have the same row and column. So 1, 1, 1 will be the diagonals, and then the rest will be 0. I4, likewise, guys, notice the diagonals are 1, and then I6, the diagonals are 1. Okay, and you recall, guys, in Excel, in order to set up your identity matrix, you have to first, for example, here, we're setting a 6 by 6 size identity matrix. Just highlight your 6 by 6 cells, and then we use the function munit. Okay, and we know that it's an array formula. We have to press Ctrl-Shift-Enter. Okay, and then we learned last time that in matrix multiplication, you can multiply a matrix to its identity, to an identity matrix, and the answer is that the resultant matrix is the matrix itself. So G times I will be equal to G, H times I will be H, or I times H will be H. So the size of the identity matrix, of course, will depend on whether it's the first matrix or the second matrix. Still, matrix multiplication rules apply. Okay, and then last time we also looked at the determinant of the matrix. We said that this is important to determine whether it has an inverse. We learned how to manually compute for the determinant of a matrix, but the shortcut is just the formula mdeterm in Excel. Okay, and we said that a matrix that has a 0 determinant will have an undefined inverse. So for example, we have matrix R. The determinant of matrix R is 13. Okay, therefore it means that its inverse is defined. And we look at that here. The Excel function is meanverse. The mean matrix inverse of matrix R. And then we said that it should be Ctrl-Shift-Enter. Okay. So we have this, the inverse of matrix R. And remember that only square matrices can have an inverse. And what's so special about an inverse, the inverse of a matrix? The inverse of a matrix is such that when you multiply it to the matrix itself, then it will yield an identity matrix. Okay? Whether it's post-multiplied, which means you multiply it after the matrix, or pre-multiplied. Okay? In this case, guys, the order will not matter. I mean, it will always be multiplicable because they are these are square matrices. Okay, so whether we post-multiply our inverse or we pre-multiply it, it won't matter. And we will always get the identity matrix as a result. Okay, and then we had an example last time. This is your matrix Q, and we determined that the determinant of this matrix is 0. So when we got the inverse of that matrix, Excel seems to return some numbers, but these are okay. This seems to be very strange numbers. In fact, the first they have the same values for the for each of the rows. They only differ in the negative sign. Okay, but the main test there is that when we multiply the matrix with its inverse, it will not give us an identity matrix. So this is not an identity matrix which validates or which violates the principle of matrix multiplication. Okay, and then last time we also had an application of matrix algebra, matrix multiplication, and we used a system of linear equations to determine the unknowns. Okay, there are so many other applications of matrix multiplication in finance, in economics, in econometrics, but we will not discuss that as of the moment. Okay, I'd like now to invite you to open your R. We were working on this file. Let me flash that screen first. Okay, this was the same file we were working on last time. And again, by way of review, we looked at different data structures. If you recall, guys, we have vectors. Okay, a vector is just a one-dimensional array, and all the elements are the same. Then we also have lists. Okay, a list is also a type of a vector. However, you can have different types. Well, technically, it's not a vector. You can have different types of data types. You can have different data types there. Okay, and then we looked at, so this was we looked at last time at, if you recall this, guys, data frames, okay? Data frames. So data frames are multi-dimensional. It can be you can have X number of rows and X number of columns, and it can take on different data types. So when we go back to when we start with ggplot2, we're going to make use of data frames. And then we also have the data structure, okay, here, matrices. So we're going to look at this now. All right. So these are some of the basic rules in matrix, using matrix in R. Data is entered by columns, okay, starting with column 1. Okay, let me explain that. And the syntax, this is the syntax. So you have matrix, this is the function, and then you give the data, and then you have the number of rows and the number of columns, and then you have this by row. And this means that if you indicate this to be by row, you put in the data in a row-wise function, row-wise manner. Otherwise, if you don't put this, the default will be the data will be inputted by columns. So let me illustrate that by an example. So here we're going to create a matrix A, and then I said this is the function matrix to create a data structure that's matrix type in R. And then here you have the combine, we concatenate. So these are the elements of the matrix: 2, 3, -2, 1, 2, 2. The 3 here, guys, represents the number of columns. Okay, and 2 here represents the number of, number of rows, 3, and the number of columns is 2. So we're asking R to create a matrix, okay, that has 3 rows and 2 columns. And how will the data be inputted? It will be inputted by columns. How do I know? The default is R will input the data via columns, because you did not define it to be by row. Okay, if you want the data to be inputted by row, then you have to include this: by row is equal to true. Otherwise, it will be inputted as by column. All right, so let's generate this. You notice that there's a parenthesis at the beginning and at the ending of the code. That means that this will be automatically printed out by R. So let me run this, Control Enter. Okay, so here you have now matrix A. Okay, so how was the data inputted? The data was inputted by column. See, 2, 3, -2, 2, 3, -2, and then -1, 2, 2, 1, 2, 2. Okay, so this code, guys, generates a matrix called A, and this is the matrix. By column 2, 3, -2, 1, 2, 2. And notice that in our environment panel, you have now matrix A. Okay, So we have created an object called matrix A, and the format of the elements of matrix A is this one. So let's first check if matrix A, if A is indeed a matrix. So we can have this code, this is that matrix A. Let's run this. Okay, then that's true. Okay, so our answer is that matrix A is indeed a matrix. Okay, and then is it a vector? Okay, it's false. Okay, so the object A is not a vector. Okay, it's a matrix. And then what's the dimension of A? So it's 3 by 2. It's a 3 by 2 matrix. All right. Now, matrices can be multiplied. Okay, so this is our, I'll just look here at our console. So this is our matrix A. You can multiply matrices by a scalar. When I say scalar, by a number. So here, we're defining C to be a number 3. Okay, so we have here the object, small letter C. It's equivalent to number 3. So can we multiply C times A? Let's see. Okay, so what happened here? Notice that we multiplied each of the elements of our matrix A by 3. Hence, the resulting matrix is C times A is, each of the elements are multiplied by 3. And is it possible to reverse that? A times C? Yes, it's the same. So when you are multiplying a matrix with a scalar quantity, it doesn't matter whether you pre-multiply the scalar or you post-multiply the scalar quantity. Okay? It's not multiplying by matrices. It's just multiplying a certain matrix by a scalar quantity. All right? Okay, so as we did in Excel, we can also perform addition and subtraction in R. And that's very easy. So we already have our matrix A. This is our matrix A. Okay. This is our matrix A. This one, we already have this. And we know it's already existing in our environment. This is A. Let's create another matrix. Let's call it matrix B. Okay. And it's a combination of 1, 4, negative 2, 1, 2, 1, 3. Number of rows is 3. Number of columns is 2. Okay, so let's define this, matrix B. All right, so you have matrix B. So can we add matrix A and matrix B? What is the dimension of matrix A? Matrix A has a dimension 3 by 2. Matrix B has also a dimension 3 by 2. So can we add them? Yes, we can. So here we're creating an object, capital C, which is equal to A plus B. Okay? And then again, the parentheses here will automatically give us the output. So there. This is matrix C, which is just the sum of matrix A and matrix B. Okay, we can also do matrix subtraction. So let's call it D. And we're just subtracting A minus B. Okay. So you can check, guys, if this is correct by just subtracting matrix A. Let's check one number. So this is matrix A, right? So 2 minus 1, okay, that gives us 1. Okay, and then you can also check whether the other elements are fine. Okay, so let's now go to matrix multiplication. Okay, we said, guys, that two matrices are multiplicable if and only if the column of the first matrix is the same as the row of the second matrix. So order is very important for matrix multiplication because matrix multiplication commutativity principle does not apply. Okay, so let's create another matrix. Okay, let's call it matrix E. Matrix E, I think it's the same as a matrix A. But anyway, let's do this. So for matrix E, let's let's change the let's just use this. Okay, so this time, guys, wait, let me just first generate this. Sorry. Let me just generate this first to illustrate the difference. All right, so first let's create matrix E. 2, 3, negative 2, 1, 2, 2. So we expect this matrix to be going down because it's by column. 2, like this, 2, 3, negative 2, 1, 2, 2. I think this is the same as matrix A. Yeah, it's the same as matrix A. So if I generate this, Control Enter. Okay, so we now have matrix E, 2, 3, negative 2, 1, 2, 2. Now, if you want this to be inputted by row, then we have to indicate this by row is equal to true because the default is by column. The elements will be inputted by column. So let's run this. Okay, so how does now this matrix differ? Okay, notice that the elements are now inputted by row. So 2, 3, negative 2, 1, and then 2, 2. All right? So if you want the elements to be inputted by row, then you should include this chunk, this function, this part of the code by row is equal to true. Okay, otherwise, if you don't put it there, then Excel, the default is that it will be inputted by column. Okay, so we have matrix F. So it's a 2 by 3 matrix. Let's generate this. It will have 2 rows and 3 columns. Now question, is matrix E, okay, which is 3 by 2, multiplicable to matrix F, which is 2 by 3? The answer is 3 by 2 and then 2 by 3. So let me just okay. So the size is, we said that matrix E is 3 by 2 and then matrix F is 2 by 3. So are they multiplicable? Yes, they are. Okay. The column of matrix E is the same as the row of matrix F, and the resulting matrix is 3 by 3. So we expect a 3 by 3 matrix. So let's go back to R. Let's use R to generate this. Because we have learned how to multiply this via Excel. So how do you perform matrix multiplication in R? So let's create a matrix G, and you have F. So here we're multiplying F times C. So let me go back there. So can we multiply F by E? Okay, the answer is, so this is F. F is 2 by 3. E is 3 by 2. Okay, so they are multiplicable. Only that FE will have a dimension, a size, which is 2 by 2. On the other hand, EF E times F, they're also multiplicable, but the resulting size is 3 by 3. Okay, so that's the difference between FE and EF, but both are multiplicable, but the resultant matrices are different. Okay, that can be easily shown because they have different sizes. Okay, so let's go back to our R. All right. So first we have F times E. Now, matrix multiplication in R is done this way. So percentage, asterisk percentage. That's how we multiply matrices in R. So percentage, asterisk percentage. So let's run this. Let's run this. Okay, so we notice that F times E, F is 2 by 3, E is 3 by 2. We said a while ago that the resultant matrix is 2 by 2. So indeed, the resultant matrix is 2 by 2. Okay. And then this can be easily also validated using Excel. We will have the same result. Okay. Now, how about E times F? So here we're creating an object called H, and then we're matrix multiplying E to F. We expect that the resultant size should be 3 by 3. Okay, because E is 3 by 2, F is 2 by 3. Yes, they are multiplicable, but the resultant size is different from the first matrix multiplication G that we did. So let's run this, Control Enter. There. So this is matrix H, which is E times F. And we can, as I said a while ago, we can manually show in Excel that this is indeed correct. Or we can also use the mmult function in Excel to show that this is correct. All right. Okay, next we go to the transpose of a matrix. So going back to our matrix A, this is our matrix A. Okay, if I click this, so this is our matrix A, 2, 3, negative 2, 1, 2, 2. Okay, that's our matrix A, which I generated by clicking here in our environment. All right, so let's go back to our code. The transpose of a matrix is very easy to do in R. So let's create an object called AT, and then the function is T, just T, guys. Transpose of A. So let's run this. Okay. So we know, guys, that the transpose of a matrix is simply the rows become the columns and the columns become the rows. So this used to be in matrix A, this is the column 2, 3, negative 2. These are the columns 1, 2, 2 and 2, 3, negative 2. When you get the transpose, they become the rows. So our 3 by 2 matrix, which is matrix A, becomes a 2 by 3 matrix. Okay. By the way, sorry, I forgot to mention to you. Okay, let me backtrack a bit here. Okay. Okay, so what do these numbers indicate? This one. What do these numbers indicate? So if you recall, guys, the brackets will allow us to create a subset of our data set. Now this one What does this mean? This, okay, is represented by, this whole row is represented, this whole column is represented by, okay, what's this? You have an empty number here and 1. So what does that mean? What does that mean, guys? This means, guys, the empty number here indicates that it includes all the rows and the first column. So it's defined by row number and column number. So this is column number 1, and it includes all the rows. This is column number 2. Okay, so this bracket, comma 2, refers to all the elements of column number 2. Okay, this is column number 2, I mean, and then all the elements of the row. So this is row 1, row 2, row 3. It includes all the row elements. Same thing here, guys. This is column number 3. Okay, it does not include column number 2 or column number 1. It only includes column number 3. Okay, via this one. And then all the elements of the rows. So this is part of row 1, row 2, row 3. So all the elements of the rows and also only column number 3. How about this, guys? Again, you have the parentheses, the bracket, the parentheses. And then you have this. Okay, sorry, the brackets. And then you have this one, row 1, all the elements, this is row 1 only. Okay, and then all the elements of columns. So either column 1, column 2, or column 3. Okay, so this is row 1. Okay, it does not include row 2 or nor row 3, but it includes column 1, column 2, column 3. So this line here is the whole of row 1, and it includes column 1, column 2, column 3. So it identifies this one as column 1, and then it did not put anything in the, it includes row 1, and it did not put anything in the column, which indicates that it includes all the columns. Same here for row 3. So for example, this element 2 is, what is a subset? How is this subset defined? It's row 2, column 2. So that's how we define the position of an element in a matrix. Okay? All right. So we now go to an identity matrix. All right. So an identity matrix, we know that an identity matrix is a matrix where all the elements, where all the diagonals are 1 and the rest are 0. So if you take a look at this one, I1. So we learned when we discussed this in Excel that I1 is an identity matrix with a square matrix, okay, with just one element, with one diagonal. So how do we write this? So using the diag function, it will give us the diagonals. So we concatenate, 1 here refers to, if you take a look at this code, guys, so we're going to concatenate, hindi lumabas yung IntelliSense. Anyway, so the diagonal function, okay, defines what will appear in the diagonal. Here, can you see that IntelliSense, guys? Diag x is equal to 1, n row, and column. Okay, so that's the syntax. First, what's the element in the diagonal? Second, the number of rows. Third, the number of columns. Okay, so if you look at this code, it tells us that the diagonal is 1, the number of rows is 1, the number of columns is 1. So 1 row, 1 column, guys, that means it's a 1 by 1 matrix. Okay, let's run this. Oops, wait. Sorry. Yeah, I think I made a mistake here. So it's a concatenation. Okay, sorry. Apologies. So this is our X. So this should be an I3. Sorry. Let's change this. This is an I3. So the diagonals will be 1, 1, 1. Okay. That will be the diagonals. We did not put anymore the number of rows and the number of columns because it's understood if you have the diagonal 1, okay, diagonals are 1, then that indicates that the number of rows will be 3 and the number of columns is 3. Okay. Apologies for the wrong explanation a while ago. So I3, guys, I3, identity matrix with it's a 3 by 3 matrix. So in R, that can be easily constructed by diagonal C. We identify the elements of diagonal 1, 1, 1. Okay. And then we did not define the number of rows and the number of columns because it's obvious that if the diagonals are 3, then there will be 3 rows and 3 columns. And when we run this, we get this. Okay, so this is an identity matrix 1, 1, 1, 0, 0, 0 for the other 0 for the other elements. Okay, then let's take a look at a symmetric matrix. What is a symmetric matrix? What is a symmetric matrix? So let me explain this by way of an illustration. So we're creating a matrix here with elements 2, 1, 5, 1, 3, 4, 5, 4, and negative 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So it's 3 rows and 3 columns. So how will Excel input these elements in your L column? It will be by in your L matrix. I'm sorry. It will be via columns, because that's a default. We did not define this to be by row. Okay, so let's run this. Control Enter. Okay, so we have this matrix 2, 1, 5. Okay, 2, 1, 5, 1, 3, 4, and 5, 4, negative 2. Okay, so what do you notice about this matrix? Okay, you notice that their mirror image. When I say mirror image, okay, so this element is first row, second column. Okay, first row, second column is 1. Its mirror image is the second row, first column. So you just interchange the row and column position. So the mirror image of 1, 2 is to 1. And you notice that they're the same. This is 1, this is 1. The mirror image of this one is this one. And they're the same. The mirror image of 3, 2 is 2, 3, and they're the same. Okay? So this is what I mean by a symmetric matrix, where the mirror images are the same. You have the diagonal, and then you have the mirror images. 2, 1, 1, 2, they're the same. Third row, first column is the same as third row, correct. Third row, first column is the same as first row, third column. Third row, second column, the same as second row, third column. So since they're all the same, guys, the mirror images are the same, then this is what we call a symmetric matrix. Okay, you can prove that a matrix is symmetric by getting its transpose. So here we define another matrix. Let's call it LT, which signifies transpose. And we use the T function, which is the transpose. Control Enter. Okay. Notice that they're the same. 2, 1, 5, 1, 3, 4, 5, 4, negative 2. Okay. So a symmetric matrix is one whose transpose is the same as itself. Okay, that's what you mean by symmetric matrix. All right, we go in now here to the inverse of a matrix. We say that this is very important in some uh, linear algebra applications and finance and econometrics. The concept of inverse of a matrix is very important. So we have a matrix here. Let's define it to be, it's a, let's make this, change this guys to J. Because we already have a matrix A. Okay, I'm going to replace all the A with J. So J. Okay, now let's first generate matrix J. There are 9 elements here. It's a 3 by 3 matrix. So elements will be inputted by columns. So you expect here to be 4, 4, negative 2, 2, 6, 2, and 2, 8, 4. That's how we expect our matrix to appear. Okay, so this is it. 4, 4, negative 2, 2, 6, 2, 2, 8, 4. Because the elements of the matrix were inputted via columns. All right, so let's get the, okay, here. How do we generate the matrix? Okay, how do we generate the inverse of a matrix? Okay, we use the solve function. Okay, solve gets the inverse of matrix of a matrix. So is J invertible? Let's check. Let's check. Because we said that, how do we know, by the way, if a matrix is invertible? I think I did it somewhere here, okay? Let's check what the determinant of matrix J is. Okay, so let's see, det, parenthesis, det, J. So we're getting the determinant of J in order to see if this matrix is invertible or not. Okay, Control Enter. All right, it's 8. The value of the determinant of J is 8. Therefore, we know that matrix J has an inverse. Okay, because the value of the determinant is not 0. Only matrices that have 0 determinants will be not invertible or uninvertible. Right? So let's create an object Ji and let's get the determinant of matrix J. So we use the solve function, Control Enter. Okay, whoops, wait. Error unexpected. Here. Okay, I think there's double parenthesis here. Sorry. I forgot to open and close parentheses so that we can automatically generate Ji. Control Enter. Okay, guys, the reason why we had an error here is because I failed to put here the open parenthesis, and yet we have a closed parenthesis. All right, so Enter. There. So this is the determinant of matrix, this is the inverse of matrix J. Okay, so we know from our previous discussion that the inverse of a matrix is a special type of a matrix because if you multiply the inverse to the matrix itself, then you'll get an identity matrix. Now we said also that it doesn't matter whether we pre-multiply it or post-multiply it to our matrix. So in this code, we have matrix J, and then we're multiplying it to the inverse of matrix J. Okay, recall that Ji is this one. It's the inverse of matrix J. This is J. So are these two matrices multiplicable? Yes, they are multiplicable. J is 3 by 3, Ji is also 3 by 3. Okay, so no problem with matrix multiplication on that based on the size. Right, let's multiply this, Control Enter. Okay, and then as expected, guys, J times Ji will give us an identity matrix. So that's the result when you multiply a matrix to its inverse. All right. How about here, guys? We multiply, we use first the inverse times the matrix itself. And as I said a while ago, it doesn't matter if you post-multiply the inverse or you pre-multiply the inverse, you're going to get the same answer. All right, so there you are, guys. Okay. So we have created here this object. No, we didn't put a name here. Okay. Sorry, we didn't identify the name of the object. Okay. Okay, this one. We have here matrix C. Okay, this is just the same example above. Let's just reinforce that this idea of inverse, matrix multiplication, and determinant of a matrix. Okay, so we're creating an object called J. Let's call this K. Let's create another matrix because we already have C. We don't want to overwrite. If we generate this object, this new object Z, then it will overwrite because we have already an existing matrix C. We have C here, guys. Okay, if we create another object called C, then it will overwrite that C. So let's just use another letter, K. Capital K, because R is case sensitive. K. Okay, so we're creating a matrix K. It's going down to 1, 6, 1, 3, 4, 6, 4, negative 2. It's a 3 by 3 matrix. So let's create this. So this is our K. And then let's get the, remember this is what? What's this? To solve for the matrix. No, the inverse of the matrix K. You should have placed it here also as a comment. Okay, just for comment purposes. All right, so we have generated matrix K. As we can see here, there's matrix K. Okay, then we solve for the inverse of matrix K. Actually, let's first try the determinant. Determinant of K to check if K is matrix K has a determinant. Okay, it's negative 102, then it's fine. It's non-zero, so it means that matrix K has an inverse. So let's now get the inverse of matrix K. So this is the inverse of matrix K. Okay, and because matrix K has an inverse, then if we multiply matrix K with its inverse, you get the identity matrix, right? So this is practically zero, guys. This is 1, okay, and the rest are 0. Okay, these are in scientific notation. We can also do the same. Okay, so it's the same, guys. Ki, the inverse multiplied by the matrix, will give us an identity matrix. I hope you're convinced, guys, that this is an identity matrix. This one, 1.11 e to the negative 16, you know that this one is scientific notation. It means that you go to the left 16 times. So that's point and then 15 zeros and negative 1. It's practically 0, guys. And this one also. And this one. Okay, so let's continue. Okay, this we already discussed, determinant of matrix. So let me just run this. So what's our C? What's our matrix C? Let me click this. Matrix C is this one, 3, 7, negative 4, 2, 4, 3. All right, we're getting the inverse of matrix C. Okay, what do you have here? It's an error, guys. Why? Here, X must be a square matrix. So C, where's C? This is matrix C. You notice C is a 3 by 2 matrix. It's not a square matrix. Therefore, as discussed in class, in the inverse of a matrix can only be there can only be an inverse of a matrix if the determinant is not 0, and then if it's not if it's a square matrix. All right, then, okay, how about concatenation? Okay, let's define a matrix here, P. So this is our matrix P, and the size of matrix P is 3 by 2, 3 rows and 2 columns. And the way this was inputted as a matrix is 2, 3, negative 2 going down by column. We know that it's by column because that's the default of R, unless you want to make it to be inputted by rows, where we add here comma by row is equal to true. Okay, I hope that's very clear to us. I have explained that several times. So let's run this. So this is our matrix P, 2, 3, negative 2, 1, 2, 2. Okay. All right, suppose I want to add another column here, or not another column. So we have here matrix Q, which is also a 3 by 2 matrix, 1, 3, 2, 1, 4, 2. So let me run this. Okay, 1, 3, 2, 1, 4, 2. Okay, now let's create another matrix. Let's call this PQH, let's call it R. So we have a matrix R, and okay, see this one, guys? C bind. C bind means column bind, which means you're going to concatenate, you're going to connect or combine matrix P and matrix Q by column. So you have P first and then Q, you're going to connect Q here. Okay, so let's run this. Okay, there. So this is matrix R, guys, matrix R. It's generated by combining column bind P and Q. That means the order of the column will be the same, okay? But it will be P first, and then we're going to add Q. If it was the reverse, okay, QR, let's call this R1. R1. So let's column bind Q, then P. Okay. So for this one, okay, what do you notice? So this is your Q. The first 2 rows are your Q, and then the second 2 rows are your P, because we have specifically stated that we're going to column bind our matrix, call it R1, and then put Q first, and then P. Now, what about if it's vertical concatenation? Vertical concatenation, you are adding by rows, okay? So let's first check what are here, R bind A and B. So let's see, what's R? See, let me check. What's our A? So this is A, it's 3 by 2, and then B. What's our B? B is also 3 by 2. So we can combine them, guys. We can combine them. We can only combine matrices if they have the same dimensions. So let's combine them vertically, okay? So that means we're going to use your R bind, row bind, which is this one, okay? Row bind, all right? We're creating a matrix called V, row bind A and B, control enter. All right, see guys? So this is matrix A, okay? And then matrix B. We put it beneath matrix B because we're adding by rows. So that's your R bind or your vertical concatenation. Okay? All right. So this was supposed to be an assignment, guys, but since I'm not allowed to give an assignment, I would request you to practice this. Okay. So let me first show you how to how to do this, and then I hope you'll practice, guys. There are 11 questions here. Okay, 11 questions, and it's good for us to practice on the questions so that we have more familiarity with R. Next Wednesday, we're going to start already with ggplot2. Okay, so kindly let me insert. Before we look at this, we want to put here discussion for Wednesday, November 25. So we'll have, we're going to start with data visualization. Download ggplot2 Wednesday. Okay, how do you download that? Let's insert this. So you know, guys, that we have to install that packages first, and then let's install ggplot2. If you haven't installed this, guys, then you have to run this. If you have installed this, then you just this coming Wednesday at least, no? To access the use of this package, we will be using this code library ggplot2. And if you have time, guys, I suggest that you look at videos on ggplot2. There are tons and tons of packages about ggplot2. ggplot2 is a very powerful package for data visualization. All right, so for your practice, guys, okay, if you run this data, okay, so let's run this data. This will give us the data that come with the packages in R. So you can actually make use of several data sets that come with R. In fact, we're going to use air passengers next meeting also. This is one of the data set that we're going to use. Okay, so that code data will give us what are the data sets that come with R. Okay, now this is not the complete one. Some packages have their data sets that go with them. Okay, so if you want to access all, so data package is equal to that packages, all that available is equal to true. So if I run this, before I run this, our data sets, okay, it does not It does not give us the number, but let me just run this. Okay. Okay, so what do you notice, guys? Did you notice that I have now more data sets? Now we'll have different answers because I have several packages already installed in my R. If I take a look at this, okay, so I have several packages already installed in my R software. Most probably don't have this, guys. So you'll have a different list of data sets as compared to the first one, okay, where I have fewer versus this second one where it lists all the data sets that come with the packages. So usually R has its package, and then it comes usually with the package are data sets that can be used by the user for practice. Okay, so that's for this second. All right, so now I don't know if you have already, so from the empty cars, guys, if you haven't installed empty cars, so kindly do that. Install that packages, empty cars. Okay, if you install that, guys, although I didn't need to install that anymore because I have it there. Okay, and then let's make use of the library empty cars, which means we're going to make use of, oh wait. Empty cars is not available for R.0.2. This must be from a lower version. Okay, wait. I'm checking if it's in my packages, but I don't think it's available at this. It means that there's no update yet as far as this package is concerned. But let me see this. Data is packages. Data. Okay, I have to check this out first, guys. It doesn't load. All right, so I have to check this, guys, because it's not working in my R Studio version. Okay. Anyway, we're going to make use. I'm going to email you. I'm going to post that announcement so that you can practice on this. So we're going to, if I'm not able to find a resolution for this, then I'm going to change the data set and then answer these questions. But by practice, it will not be collected because I don't think I can give assignments for this week because it's academic easing. But I encourage you to practice, guys. So how do you view the first 10 rows? Do you recall the command for this? Remember this, guys, the head. Okay, the view the last 10 rows. Okay, use the tail function. Okay, determine the class structure, how many rows and columns. Okay, use code to generate the 5-number summary. All right. So these are the things that I want you to try to answer, guys. Before we have our, before we begin our class session next meeting on ggplot2, we'll answer this first. Okay, and then and then we proceed to ggplot2. Okay. So I think we have covered what I need us to cover today. I'm not going to use the full 1.5 hours. I'm just going to cover whatever up to the last point of the lesson. Okay, so that's about it for today, guys. I'm going to upload this, and please feel free to PM me or to ask questions. Email me if you have questions. All right. So, okay. Thank you very much, and you have a safe day, guys. Okay. So, salamat lang ako, guys.
Thank you, sir.
Thank you. Thank you, guys, ha. Ingat kayo lagi, ha.
Sir.
Sige, salamat.